This is geometry, unit 6. We're talking about standard position. When we do coordinate proofs, we need to be able to place a figure in a coordinate plane in a standard position, which is going to be in quadrant 1. To be in standard position, we need to have a point at the origin, and we want to use the least amount of variables. We want to try to minimize the variables. So we're going to come over here to a square, and we placed a point at the origin, 0, 0. We placed a point on the x-axis. If this is a square, then we need to be the same distance up as we were sideways for a square. And to find our fourth point, we need to go straight up and straight over to find our location. That has to be at exactly that location if those points are fixed. So this length here can be any amount. If we want to consider it to be 1 centimeter or 2 centimeters, that's great. 10 centimeters, 5 feet, whatever it is. We're going to call it a length of A. So this coordinate is going to be A, comma, 0. That means that the A can represent any number value. If it's small or big, it doesn't matter. It's A, comma, 0. The 0 tells you you're on the x-axis, and the A means you're in the positive direction away from the origin. Our other point over here has to be up some amount. Think about what a square requires. A square's got to have all the sides the same. So if this length is A, whatever this length has to be the exact same. So this is going to have to be 0, comma, A. 0 because the x value right and left is 0 because we're on the y-axis, and we're up the same amount we went over. That's what a square requires. So it's 0, comma, A. Next we're going to be talking about our final point. What's the coordinate of this final point out here?
AA.
We've got to be over the same amount, and we got to go straight up the same amount. So if we went over A and we've gone up A, then this coordinate has to be A, comma, A. And from here, you should be able to do distance formula, midpoint formula. You could look at the diagonals. Lots of different calculations we can make, and they have to support what a squared would be. Let's talk about a rectangle. We all know that a rectangle is a special type of parallelogram. The only requirement about a rectangle, besides it being a parallelogram, is that it has to have 4 right angles. We know that every parallelogram has opposite sides that are congruent. So in this case, we have our purple sides, they're the same, and we have our orange sides, they're the same. But they don't all have to be the same. They can be different next to each other. That's what's special about a rectangle. So if we were to draw a rectangle in standard position, we know we're going to put a point at the origin. We're going to come over here and label this location. what coordinate value should we give this one out here? A comma 0 would be our typical value that we give our x-axis. Some distance over, this distance is going to be considered A, so this point is labeled as A comma 0. In a rectangle, notice, this horizontal side length and the vertical side lengths, they don't have to be the same. So what coordinate value should we give this point? 0, because you're on the y-axis, it's 0 right and left. Up, something different than A. We don't have to have any relationship to the A. So we'll call this B. That's different than the A. But this final point, think about the final point that we're drawing. To make this a rectangle, does that final point have to be at a specific location? It has to be straight above what this point was. And it has to be straight over at the same height as that one. So what's our coordinate going to be for a rectangle? The length here is A, so the x value is A, and the height is B. So that's A comma B. Next, we're going to look at an isosceles triangle. Do you recall what an isosceles triangle is? An isosceles triangle requires two sides to be the same. In fact, an isosceles triangle, by definition, it is at least two sides. So even if you had all three sides the same, that would be isosceles also. But typically we give that a special name called equilateral. This is an isosceles triangle where we have at least two sides exactly the same. So of course we're going to have a point at the origin, 0, 0. We have a point anywhere out on the x-axis. And we would probably, don't finish this off yet, just put down the A, and you can put down the comma 0. Don't worry about the parentheses quite yet. So we, of course, would call that A comma 0, because it's some distance off to the right. If we're going to think about our isosceles triangle, this point we have learned before, for it to be equal distance to the endpoints, this point up here has to be on what's called the perpendicular bisector. So what we have to do, we have to bisect this right down the center. We have to go up at a perpendicular direction, any amount we want. It doesn't matter where we go. So if we have to be on the perpendicular bisector, then we have to be half the A value, because we need to cut this distance in half. So instead of calling this just A, let's get crazy and let's call this 2A, because we know that we're going to cut it in half. So that's why I suggested not to put parentheses around it yet and give us a chance to write the 2a in front of it.
Why are we doing it like this? Because wouldn't it make more sense if we just like use the like right angle and then...
So if this is 2a all the way out to the side and we're on the perpendicular bisector, then we know that this distance here is just going to be a. Now, if that wasn't confusing enough, what height do you suspect we're at? Do we have to be up a certain amount? Is this an isosceles triangle? Is this an isosceles triangle? It's just a little bit taller now, huh? Is this an isosceles triangle? All those points are on the perpendicular bisector. So you can be an isosceles triangle, and this point could be really anywhere. It could be called a variable of y, but since we're doing letters near the a, let's typically call this b. But y would not be horrible, since it's the y value, but we would typically call that b. You're up any amount that you need to. It's not related to the a at all. So that's why we call it b. But the x value is related to how far we went over. We have to go over half the amount, so that's why we want the 2a and the 1a to be related to each other. All right, so those are our coordinates. So from here, we could do distance formula. We could look at slope. We could make some arguments about why this is isosceles. Let's look at an equilateral triangle. An equilateral triangle, of course, has all three sides the same. So it would be something like that. All three sides are exactly the same. So this point's not super important. But that point is somewhat related to how far over you went. You can't go up any amount that you want. It would no longer be isosceles. Or we're trying to be equilateral. Remember, equilateral is a type of isosceles triangle. It has at least two sides the same. In fact, an equilateral has to have three sides the same. So we're going to draw our side length, and then we'll try to figure out where this next point is so it looks like all three sides are the same length. And that seems somewhat reasonable. I bowed this one a little bit. Seems a bit better. Okay, what are my coordinates going to be? Of course, this one is 0, 0, because it's at the origin. That's the easy one. This is some distance over. But since it's a type of isosceles triangle, we're going to use the variable 2a, because we want it to be able to cut that in half. Right? On the perpendicular bisector means our two sides are going to be the same length. if you're on the perpendicular bisector. So that means this location has to be half of our 2a. So if you put 1a there, you just have to use a fraction of 1/2 the a. But so we don't have the fractions, we just call this 2a. So this could be 1a, half the 2a. At what height are we at? Don't we have to be at a perfect height? We can't be up any amount that we want. Otherwise, these lengths would not match the 2a length. So we have to look at this triangle right here. That triangle has a side length that is supposed to be 2a, and the short leg is supposed to be half of the 2a, so that would be a. The question is, what is the height? What is the height of this triangle? So we can use Pythagorean Theorem, since this is a right triangle. Hypotenuse squared equals leg squared plus leg squared. When you square 2a, you get 4a squared. Now, if we're trying to figure out what the h value is, we need to collect some like terms. So what are we going to do from here? How are we going to isolate the h squared? We're going to have to subtract the a squared across. So now we have 4a squared minus 1a squared, which gives us 3a squared. Now that 3a squared equals the h squared, and the h squared, you could take the square root of it. So we're going to take the square root of 3a squared. We're only considering the positive version of the square root. So we're not going to write down plus or minus. When you take the square root of both sides of an equal sign, you've got to have plus or minus. But since this is geometry, we're not going to consider the negative version. We'll just imply that this is a positive square root. Do I know the square root of 3? Well, it's some decimal number. Do I know the square root of a squared? What times what being the same exact thing makes a squared? A. The square root of a squared is a. So this would be a, the square root of 3. That is your height. So our coordinate here, make a little bit more room, our coordinate is going to be a root 3. You're going to see that come into play more in the future also, when we do our special right triangles. So we have 0, 0, 2a comma 0, and this crazy location called a comma a root 3. Let's talk about a scalene triangle. What do you know about scalene triangles? Scalene triangles are going to have 3 sides, different lengths. So notice I don't have, I almost do, but I don't have that point on the perpendicular bisector. I have it off the perpendicular bisector. So since I'm not going to be half of this amount, I can go back to a comma 0. So if I'm not at half that a, what are we going to call the amount that we're going to the right? B. And in an isosceles triangle, does it matter what height I go? Does it have to be a certain location? Is it related to the A? Is it related to the B? And the answer is no. It is a different location. It has a different height independent of the other variable. So that's why we change its variable up, and it's going to be C. And this one, of course, is 0, 0. So from here, we could find the midpoint of our sides. We could do the slopes of our sides. We could do the distance formulas of our sides. You can do some math based off of those coordinates, which should be true about any triangle that is isosceles. All right. Or any triangle, I'm sorry, that is scalene. This one is isosceles. This is called an isosceles trapezoid. Do you know what an isosceles trapezoid is? Trying to make this look like an isosceles trapezoid can sometimes be a challenge. So I have a point at the origin. That's automatic. I have a point on the x-axis. Now, this third point that I place, does it matter really where I put it? It's just got to be in the first quadrant somewhere. Doesn't overly matter how far to the right I go, how far up or down I go. I'm going to place this dot. Now, when I think about my fourth vertex, does it matter where I place it? I do have to place it at the same level that is parallel with this side. So we know that. Now finding the horizontal distance over is a bit of a challenge. Here's a trick. If you look here at this triangle, I don't want to make it real dark because it's just an imaginary triangle. But if we look at that triangle, we need to match that triangle on this side. For that to be truly an isosceles triangle, an isosceles trapezoid, sorry. For this to truly be an isosceles trapezoid, these two triangles have to be exactly the same. That tells me exactly where this point has to be. Those two triangles have to be the same. So, of course, this is going to be 0, 0. This coordinate's going to be a comma 0. Some distance over. No distance up. Now, this one, this is not on the perpendicular bisector. It doesn't have to be half of the A. It can be over any amount that we wanted it to. It could be up any amount we needed it to be. It didn't matter. Now, what about this one? How far over is this really? How far over did we come? Well, what height is it at? It's definitely parallel to the x-axis, so it has to be at the same height as this one. So we know that it's at a height of c. But the big question is, how far to the right of the x-axis is it? We know it's past the b, but we know that it's not all the way out to the a. It is going to be all the way to the a, but then we're going to have to back up, right? Isn't this value b across there? Isn't this value c up and down? Well, this would be c up and down. This would be b right here. So we're going to go the total a amount, but we're going to back up the b amount. So nice job. A minus b. And that gives us the rest of our isosceles trapezoid. And with that, we could do slopes to show our bases are congruent, or our bases are parallel. We could do distance formula to show that our legs are the same length. Last one. You go ahead and take a moment, think about example number 2, read the terminology. What is it asking you? What are the coordinates going to be? Give that a chance. Remember that vertical means up and down, horizontal means right and left. Pause the video, give it a try, come back and we'll talk you through it. Place a rectangle in the coordinate plane so its vertical side length has a length of a. So that means it has to be 0, comma a. If it's a vertical, it has to be the y value, up any amount that you want it to go. And it's horizontal, which is the right and left distance, has a width of 2a. So I'm trying to make it twice as long as I did high. So this is 2a, comma 0. We have a point at the origin, and our fourth and final point has to be straight above the 2a. So it has to be 2a, and it has to be at the same height as a. So those would be your coordinates